Okay, so in this video I'm going to have a look at adjacency matrices. So a matrix is just an array of numbers in rectangular form. So for example, we could have a matrix looking like this. Let's say 1, 2, 3, 4, 5, 6. So we have this rectangular array of numbers, usually enclosed in two square brackets. And you can see here we've got three rows along this way, and we've got two columns along this way. So this would be a 3 by 2 matrix. So generally matrices are defined as n by m matrices, where the n will give you the number of rows and the m will give you the number of columns. So we're specifically going to look at adjacency matrices, which are matrices that will give you the number of edges from one vertex to another. So let's do an example. Let's say we have the following graph. So let's say we have A here, B here, C here, D here. So we have A, B, C and D. Let's put a loop here at D, and let's connect B to D and B to D again. So this is our graph. Let's draw an adjacency matrix for this particular graph. So the way we start this is we'll just write down our vertices A, B, C and D this way. We'll draw a square bracket here. We'll put A, B, C, D along here. We'll close off our matrix with another square bracket. So the way you're going to work this is you're going to work from left to top. So you're going to work from the left hand side here to top along this way. So first thing we want to do is see how many edges are there from A to A. Well, there are no loops here, so there are no edges from A to A. How many are there from A to B? Well, we can see here that there is one edge down along this way from A to B, so we put 1 here. How many from A to C? Well, from A to C there are no edges, no direct edges anyway. And how many from A to D? Well, there is 1 direct edge. So how many then are there from B to A? Well, from B to A there's 1. From B to B, none. From B to C, there's 1. And from B to D we can see there are 2. There are 2 edges from B to D. Okay, so what about C then? From C to A there are none. From C to B there's 1. From C to C none, and from C to D 1. And finally then from D to A. From D to A there's 1. From D to B there are 2. From D to C there's 1, and from D to D there's 1. There's 1 loop here from D to D. So this here would be our adjacency matrix for this particular graph here. Just gives you the number of edges connecting these vertices here, A, B, C, D, with these vertices here. Okay, from this you can see that this matrix here is what's called a square matrix. So this is a square matrix. And again, in previous videos I have done a little bit on square matrices and how you multiply them and so on. If there was no loop here, in this particular case, we wouldn't have this particular value down here. So you can see the diagonal here would then be all zeros. So just to do an example quickly of one of those type, let's take a simple graph. Let's take let's just take a square here, and again we'll use A, B, C and D. So our matrix then, our adjacency matrix, will be A, B, C and D again. So we can just put A, B, C, D along here, and you can see from A to A there are none. From A to B 1. From A to C none. From A to D 1. From B to A 1, 0, 1, 0. 0, 1, 0, 1. It's kind of symmetrical here. So you've got 1, 0, 1, 0 here. Now in this particular graph here, there are no loops. So you can see that the diagonal is made up of zeros here, because no vertex has an edge that comes back to itself. There are no loops in that particular one. Okay, so what this also gives you is the number of walks of length 1 between any two vertices. So for example, if you take A and B here, how many walks of length 1 are there between A and B? Well, there's only 1 here. How many walks of length 1 are there between C and D? Again, 1. C and D, there is 1 here. If we go back here to our previous matrix here, how many walks of length 1 are there between B and D? Well, if we look at B and D here, there are 2 walks, this one here and this one here, of length 1 between B and D. Let's have a look and see how many walks there are of length 2 between these vertices. So how would we do that? Well, you just simply multiply this matrix here by itself. You just square the matrix. So let's have a look at doing that. So we take our matrix. I might just copy and paste it here, be easier. So we're going to multiply these two matrices here. We're going to multiply this matrix by itself. We're going to square this matrix here. Now I have done videos on multiplying out matrices, and I would just encourage you to have a look at those. But basically what you end up with when you square those is 2, 0, 2, 0, 0, 2, 0, 2, 2, 0, 2, 0, 0, 2, 0, 2. And again, if we put our A, B, C and D here, and our A, B, C and D here, you can see then we can look at how many walks of length 2 are there between, let's say, A and A. Again, start on the left hand side and go to the top. Well, between A and A, let's see if we start here. So we're starting here. How many walks of length 2 are there? Well, we can go down here to B and back again. That's length 2. Well, there's 1 walk of length 2. We can go over to D and back again. That's length 2. So there are 2 walks from A to A. Let's say A to B. Well, how many walks are there of length 2 from A to B? Well, we can go from A to B. That's length 1. But we have to go away from B then for our second length, if you like. So there are no walks of length 2 between A and B. Have a look at A and C then. Well, A and C, well, here's A and C here. We can go across to D and down, that's length 2. We can go down to B and across to C, that's length 2. So there are 2 walks of length 2 between A and C. And similarly with the other ones, I mean, if we take, let's say, B and A, well, B and A, there are no walks of length 2 between B and A. You go from B up to A, and then you have to go away from A for the second length, so there's only a length 1 here really. Or a length 3, you could go across, up, and back again, that's length 3. But we're only interested in walks of length 2. So what about B and B then? Well, same thing, you can go over to C and back again, that's length 2. You can go up to A and back again, that's length 2. Between B and C, again, there's only walk of length 1 or 3. What about B and D? Well, you can go across to C and up, that's length 2. You can go up to A and across, that's length 2. So there are 2 walks of length 2 between B and D. So in order to find out the number of walks of length 2 between these vertices here, you just simply square your original matrix. And if you want to know then about walks of length 3, you would cube this matrix here. In other words, take this matrix here and multiply it again by this here, and that will give you the number of walks of length 3 between the vertices. So to have a look at another one, let's take this one here. Let's say A is here, B is here, C is down here. So we'll just do 3 this time. A, B, C, and we'll put a loop here. First of all, let's draw the basic matrix. So you've got A, B, and C. We have A, B, and C here. This again is a square matrix, so how many walks are there, how many edges are there between A and A? There are none. Between A and B, 1. How many walks are there between A and C of length 1? There are none. How many walks of length 1 are there between B and A? Between B and A, well, there's 1. Between B and B, you can see there is 1 as well, this loop here. And between B and C, well, there's 1. Between C and A, there are none. Between C and B, 1. And between C and C, none. So we're just looking at lengths, edges, just one edge. We're just looking at walks of length 1, if you like. So if we square this matrix here, then that'll give us the walks of length 2. So I'm going to take this matrix here, 0, 1, 0, 1, 1, 1, 0, 1, 0. Multiply it by itself. So again, 0, 1, 0. 1, 1, 1 here, and 0, 1, 0. So when you multiply these two together, you should get 1, 1, 1, 1, 3, 1, 1, 1, 1. Now again, we put A, B, and C here, and A, B, and C along here. So let's have a look at this particular matrix here. This is our original matrix squared. So let's see, how many walks of length 2? Now this represents the number of walks of length 2 between the vertices. So let's have a look at the number of walks of length 2 there are between A and A. And there's only 1. So we can go from A out to B and back again. So that's a length 2, and there's only 1 of those. What about A and B? Between A and B of length 2, well, we can go from A to B and then around the loop to B, and that's the only one of length 2. So there's 1 of those. What about A and C? Well, we can go over to B and down, so that's length 2. We could go A, B, around and down, but that's length 3. What about B and A of length 2? So what we could do is go around the loop and across here to A, that's length 2, so there's only 1 of those. B and B now, so how many walks are there of length 2 from B to B? And there are 3 of them. So we could go across to A and back again, that's length 2. We could go down to C and back up again, that's length 2. And we could go around to B and around to B again, so that's a third one of length 2. What about B and C? Well, there we can go around and down, so there's just 1. What about C and A? Well, up to B and across, that's 1. C and B, we can go up to B and around the loop, that's 1. And then C and C, well, we can go up to B and back down again. So that's our, there are adjacency matrices for our graphs. And now we can also look at digraphs. So for example, if we have this digraph here, again, I'll just do this square here. And we have A, B, C, and D. And let's put an edge here and an edge here. Now in digraphs, then you've got to put in the arrows, the directions. So let's put a direction here. Here, let's put 2 arrows here, across this way and up along this way. So when you're doing this, you need to take into account the direction of the arrows. So let's do that. So we have A, B, C, D, A, B, C, and D. This is just walks of length 1 again. So let's go from A up to A here. So there are none. From A to B, there's 1 here. You can see it here. From A to B, the arrow's in the right direction, so we can put 1 in here. From A to C, there are none of length 1, and from A to D, there are none of length 1, because from A to D, the arrow is going in the wrong direction. So let's have a look at B to A then. So B to A, none, because the arrow is in the wrong direction. B to B, none, there's no loop there. B to C. So now from B to C, the arrow is going in the right direction, so we have one there. And from B to D, we have two. Both of these edges here, or arcs here, are pointing in the right direction, so we can put 2 in there. So from C to A, there are none. From C to B, there are none. The arrow's in the wrong direction. From C to C, none, no loops there. And from C to D, the arrow is in the right direction, so we have 1 there. From D to A, there's 1, the arrow's in the right direction. From D to B, there are none because the arrows are in the wrong direction. From D to C, I should say, from D to C, none, arrow is in the wrong direction. And from D to D, none there are no loops. So that would be an example of an adjacency matrix for a digraph. That's really it for adjacency matrices in this video.